So this week we're going to be talking about how limits relate to infinity, and there's kind of two different ways to think through this, uh, because we have how many different variables, right, in an equation, generally speaking. I think usually two, right? Your x variable, which is your independent variable, your y variable, your dependent variable, or the way we like to think about it, your horizontal variable, your vertical variable. Well, what this tells us is that because we have two dimensions, right, we probably have two different ways to approach infinity. And so what we're going to examine as we go through this is what happens when x approaches infinity. Okay, so that's taking the limit of the function as the domain is approaching really, really large or small numbers. That could be plus or minus infinity right there. Okay. Um, what happens is as x gets really huge, f of x is either going to probably blow up towards positive or negative infinity itself, or maybe it's going to converge to a specific constant value. There is a third fairly common possibility, which we see with our trig functions, where you have a periodic function that's either oscillating like sine or cosine, or repeating the same shape like a secant or cosecant or tangent. But for the most part, we're either going to diverge or converge as you move out towards infinity, right? What's happening is x goes to infinity. So then the other possibility, I guess, would be what happens if y goes to infinity. So this time, you'll notice the x's are not approaching infinity. The x's are approaching a very specific value. In this case, we're just calling it, c. But what we're going to find is when we get near that value, the y's are blown up. F of x is either going way up or way down. Okay, and so those are the two different cases that involve infinity in functions. And we've actually talked about all of this back in the first half of the semester when we were still in school, and we didn't use it with limits, but we definitely used it, and you'll see a lot of very familiar ideas popping up today and tomorrow. So let's start with the x's. What do we mean when we talk about x going to infinity or negative infinity? Well, when we talk about x approaching infinity, what we're really talking about, right, is our x's go way, way out to the right and way, way out to the left. What we're really talking about is end behavior. And like I said, something we did spend quite a bit of time discussing um, in um, in the first half of the semester. What types of end behaviors do the different functions have? Is it diverging? Is it converging? Is there a horizontal asymptote? Is it up, up, down, down for polynomials, down, up, etc.? And that all comes back into play here. So this first little box just talks about what we mean as far as finite limits as x approaches plus or minus infinity. Now notice we're not talking about infinite, so we're not talking about the diverging cases here, but just the converging cases. So s x approaches positive infinity if f of x is moving further and further along the right and approaching a finite number, or as x approaches negative infinity, if f of f of x is moving towards a constant value the further that x moves to the left. So x is moving way to the right and way to the left. If we're just approaching a constant number, we call that converging end behavior. And this is a great example of a function we saw many, many times early on. This is the reciprocal function, which is the parent of all rational functions. And so once again, what is the end behavior of this function? Let's take a slightly closer look at example 1 here. We know this function pretty darn well. We know that we're not allowed to put a 0 in. because that would be undefined. And that created a vertical asymptote at x equals 0. But we also knew that we're not allowed uh, to get very big with this function as we move out, because when you take really, really big numbers and put them into the denominator, you get really, really small fractions. If you take 1,000 and put it into this function, 1 over 1,000 is a tiny little value, right? And the further out you go, the smaller those values get, which means that those values are collapsing towards 0. This is something that we talked a lot about with the rational function unit in Unit 1, was who wins the battle of power, the numerator or the denominator. And anytime the denominator was more powerful than the numerator, we knew that that entire fraction, that entire rational function was going to collapse to 0. And that's exactly what we see happening here. Now, this is not something that you can plug in and substitute and evaluate or even do algebra tricks with. This is something where you just have to understand that same principle that we learned back in Unit 1, that when the bottom of a rational function is more powerful than the top, it's the rational function, as long as there's no end behavior shift to plus or minus, is going to collapse to 0. What that creates is a horizontal asymptote, right? A horizontal asymptote. And that is a huge property of limits. It was difficult to really define horizontal asymptotes early on in this class, because we knew what they were, and we knew what they were on a graph, but we didn't really have a strong mathematical way to describe them. Well, now we have a much better way, and that's using limits. So the definition of a horizontal asymptote is simply a line y equals b, where b is just a constant value. So b could be the x-axis at y equals 0, but it could be any horizontal line. As long as b is a finite constant value, then we will have a horizontal asymptote if the limit of our function towards positive or negative infinity has a limit of b. If the limit as we approach positive or negative infinity is b, there will be a horizontal asymptote at that location. So this example is really the same as example 1, except we added a 2. Okay, so just a reminder, this is still going to collapse to 0 the further out we go, right? But now this 0 is going to be added to 2. And what's that going to do? It's going to take our horizontal asymptote and just kind of shift it up 2 units is all it's going to really do. And here we have some tables that are going to confirm this, right? As we go further and further out with these x values, right? Look what's happening with the y values. They're not getting bigger. In fact, they're getting smaller, but very slightly smaller. They're getting closer and closer and closer to a value of 2. Can they ever actually get all the way to 2? No, they can't. But they can get as close as we want. If we want to be between, within 0.00000001, we just have to go out far enough to make that happen. The same thing in this case happens to the left. As we look at the left part of this graph, we're also approaching 2, but notice we're approaching 2 from below. So we're coming up from below 1 and getting closer as to 1.99, 1.999, and so on. Now, I do want you to understand you don't always have to have the same horizontal asymptote in both directions. And in fact, you don't even have to have a horizontal asymptote in both directions. That's why it breaks it into 2 different cases, case 1 and case 2. If one of those happen, there will be a horizontal asymptote for your function. But in a lot of cases, like this case, it does occur in both directions. Example 3 is a great indication where we have 2 horizontal asymptotes, 1 in each direction. And it's because of this little trick here. What we do with the denominator is we square the values, which guarantees they'll be positive, and then we take the square root of them, which kind of puts it right back to x. I mean, the overall power of the square root of x squared is really just x, but by squaring them, we guarantee positive value. On the other hand, the top, which is also has a value of x, right? Well, that could be positive or negative. So in the right direction, we're always going to get a positive basically divided by itself, just a little bit more than itself actually, but pretty much itself. So we're going to get a lot of ones, or getting closer and closer to ones. But in the negative direction, we're going to get a lot of negative values divided by positive numbers very, very close to the same value. So we're going to get very close to -1. And in fact, we get so close to -1 that in these cases, the calculator can't produce any more decimals closer. And by the time we get up to 400, it's basically saying you are 1. Now, that's not true. We can never actually equal 1, primarily because of this tiny little difference between the top and the bottom, right? But you can get as close to 1 or -1 if we're going to the left as you want. So there's two horizontal asymptotes for this problem. And once again, the reason is because of these limit statements. Look at these limit statements, because it is the new part. The horizontal asymptotes aren't really new, but the limit statements are new. As we approach positive infinity, the limit of our function is +1. As we approach negative infinity, the limit of our function is -1. Okay, and that's how you write horizontal asymptotes using limit notation. Um, these these are the properties that we looked at last week for limits in general. It was actually out of the textbook. They actually called it a theorem. We're not really talking about theorems in our workbook, but we call them properties. And these limit properties basically said that if you have a couple functions approaching the same value, that you can add the functions by just adding limits. You can take the limit of the difference or the product or the quotient of the functions just by, once again, subtracting or multiplying or dividing the limits, right? Well, as it says in your course pack, the same properties for x approaching positive and negative infinity work as approaching a constant value c, because these were all for constant values. These were all for, x is approaching c. Well, the same properties work for approaching infinity. So this, out of the textbook we're using the material from, is theorem 5. They weren't put in your workbook because they really were just repeating the same information, but it's just something to keep in mind, that these same properties work even when x is approaching positive or negative infinity, assuming that the functions do have a finite limit. As long as L and M are finite. It doesn't work if the y values are approaching plus or minus infinity. It doesn't work if the functions are diverging, so to speak. So here's example 4, which kind of borrows from this property. We have a kind of a trig thing, and this looks very similar to some problems we saw last week, except last week we were approaching 0, right? So when I split the fraction right here, and then split the limit right here, the limit of 5 is 5 no matter what you're approaching. Even if I'm approaching infinity, the limit of a horizontal value is still going to be a horizontal value. How about that? So that's just going to be 5. This is the piece right here. This is the piece right here that is a little different, because we're used to the limit as x approaches 0, not as x approaches infinity. So let's go back to the same graph that we looked at to develop this identity last week and see how it changes. This was the graph of the sine of x over x, and sure enough, as we approach 0, we approach a height of 1, okay? But what's happening as we approach positive or negative infinity? Well, this is called a dampening function. What that means is it's going to continue to oscillate forever, but every time that you pass the x-axis, you go a little less far away than the time before. See, this is a little less far away, and this is a little less far away than that. The amplitudes continue to decrease as you move further and further away. And so what that means is that you're going to continue to squeeze closer and closer to the x-axis, which has a y value of 0, right? And so even though sometimes you're a little above 0, sometimes you're a little below 0, the distance away will always continue to get smaller and smaller, which means the limit, whether you're going to the right or the left, right? Whether we're going to the right or the left, the limit of the same identity we used last week when we approach plus or minus infinity equals 0. So that's your second trig identity, and really your last one that you'll need to know regarding these limit problems. But what it does for us here is it means now that I know that this guy right here, by substitution of an identity, is just a 0. And so we end up with 5 plus 0. Now you could also make a end behavior argument out of this, and boy, we're going to talk about end behavior and models in great detail tomorrow. But it's going to kind of look like this. What's more powerful, the top or the bottom, right? And I will try to put something together to remind you the power structure of functions, because it was on our whiteboard for like the last 2 months, but now we can't look at our whiteboard anymore. But we knew that like in the dead middle was just good old x, right? But then x squared or x cubed was more powerful than that, and then exponential functions were more powerful than that. On the other hand, root functions were weaker than linear functions, and logarithmic functions were even weaker than root functions. And then the weakest of all were constant functions. Constant functions, never grew or went down. They didn't have change. Well, it turns out that sine of x is basically at the same weakness level of a constant function, because sine of x is bounded. It never has an upper bound of 1 and a lower bound of -1, and so it basically, in terms of weakness, is as weak as a general constant function. So what we're talking about here is a rational function that's really weak on top and stronger on the bottom, which means that this whole thing, based on our end behavior model arguments, will collapse to 0, which is another way you could come up with the same argument. But that is an identity that you now have. So you might jot that one down right next to the other one. So how do we analyze this? Well, we could take a look at the graph. Look what happens when we get further and further out to the right. In this case, it continues to go up and down, up and down, up and down, right? But it's definitely closing in on this horizontal asymptote at 5, which is exactly what the limit evaluation told us it was going to do, right? The limit as we approach infinity was a 5. Now, the table tells us the same thing, but it's a little weirder, because as I go 100, 200, 300, over here, look at those y values. So sometimes they're just a little below 5, then sometimes they're just a little above 5, and like this one's even closer than this one, right? Because of the oscillation, you never know exactly when they just crossed the x-axis and they're really close. But we know that the further out we go, it's going to move further to the right. It'll have smaller distances from the x-axis. The amplitudes basically continue to decrease infinitely, and that's why we know that that's going to eventually get us close to 5 as we want. So a little bit different because of the oscillating nature, but that's example 4. And so now that we're done talking about x's moving to infinity, let's talk about y's moving to infinity, or negative infinity. This time your x's are going to be moving towards specific constant values. A, maybe that's a 0, maybe that's a 2, whatever, right? And the y's are what we want to pay attention to. Now, we're going to use the same exact linear function that we used before, f of x equals 1 over x. But this time, instead of examining the end behavior as x approaches plus or minus infinity, we're going to actually examine what's happening as these approach 0. And as we approach 0 as a two-sided limit, this is something we learned last week, the limit doesn't exist, because limits have to be real numbers and they have to be approaching the same real number. And this graph is definitely not doing that. So the limit as we approach 0 for this function does not exist. But if you want to examine vertical asymptotes, you have to take one-sided limits as you approach these infinite discontinuities. And so that's what we do with this graph. Now, check out the right the right limit as we come in with this blue part of the graph, blue branch of the graph, what's happening as we get closer and closer to zero. And by the way, we're getting closer as we go up the table, right? Well, we start off with fairly big numbers like 166.67, 200, 250, but those numbers are only increasing. They're only getting bigger and bigger, and they're only going to continue to do that as I get infinitesimally close to zero. Same thing coming in with the left branch, the left end behavior, right? The left limit. I said end behavior, I meant the left limit as we approach zero. So what's happening as these x values get closer and closer to the zero from the left? And you can see same thing, except they're negative numbers. The negative numbers are increasing in value, and so we're approaching negative infinity. And that's what these limit statements mean. Okay, what these limit statements tell me, this one right here and this one right here, is that I have a vertical asymptote. I have a vertical asymptote at zero because as my function is approaching zero, the y values, the values of f of x are going through the ceiling. They're approaching plus or minus infinity. And so that's what vertical asymptotes are giving. And that's the definition of a vertical asymptote, all right? If you have a function that approaches a value from the right or from the left, and the values are approaching plus or minus infinity, then you are going to have a vertical asymptote. That's the indicator of that. In your notes, I have a little warning, and it's probably too small to read here, so I'll blow it up for you. It is a bit tenuous to describe a limit s infinity, because as we remember from the definition last week, right, a limit must be a real number. Now we can describe one-sided limits at vertical asymptotes as approaching plus or minus infinity, and that's just describing the behavior of the graph at that infinite discontinuity, at that vertical asymptote, okay? But truly, the limit doesn't exist because infinity is not a real number. So I know that that's a little bit of a stretch to talk that abstractly, but what we're basically saying is we will allow for you to write your answers at vertical asymptotes as infinity or negative infinity if it's a one-sided limit. And if it's a diverging graph, as we'll talk about tomorrow, you can sometimes describe end behavior in terms of infinity and negative infinity. But that's really about the only time that you're ever allowed to write infinity as the value of limits. So just something to keep in mind. Now, example 6, very similar to example 5, except this time instead of 1 over x, it's 1 over x squared. So we're going to get faster growth, and both branches will be positive because we're squaring those negatives. But you can see that as we approach zero from the left and the right, we're approaching really, really big numbers. This time even faster, right? This time even faster than before. And so that is definitely going to create a vertical asymptote at x equals 0. The last example just says, sometimes you can have infinitely many of these vertical asymptotes, and brings up our friend, the tangent function from last semester, which we know has vertical asymptotes at every odd multiple of pi over 2. That was the domain of tangent. X was all real numbers except for odd multiples of pi over 2, because every time we had an odd multiple of pi over 2, right? Negative 3 pi over 2, negative 1 pi over 2, pi over 2, 3 pi over 2, 5 pi over 2 would be the next one. We knew that we were going to get one of these vertical asymptotes. And this is just basically saying, hey, look, this is how you can describe them. You can say that as long as A is an odd multiple of pi over 2, then if you approach that asymptote from the right, okay, so A from the plus side, A from the right, we're going to be moving down towards negative infinity. And if we approach that asymptote from the left, you can see the little negative with the A this time, we're going to be approaching positive infinity. So it's just really old news today. Vertical asymptotes, horizontal asymptotes, we're just learning how to use limits to describe them. So hopefully for the most part this made sense. Sorry for the late upload of it, but like I said, for some reason the first time I did this I got no sound on it, and that was annoying. I'm really excited I got to say it all again. Let me know if you have any questions at at 3 o'clock, but until then, have a good day, and we'll talk to you tomorrow.